Hello? Yeah, hi everybody. My name is Akshay. I'm the third speaker of this Moire in IISc Bangalore session. Unfortunately, the speaker after me, Arijit, is not from IISc, but we'll give him honorary citizenship, followed by Pavan as well. Okay, good. So let me get started with my talk. So what Anindya and Chandan did was they laid a very nice background for me to work with, and they did a lot of transport, right? Chandan did show some Raman spectroscopy, but what we'll do now is really look at detailed optical spectroscopy in these Moire systems. And we are very excited about excitons in these systems, and then we will also introduce this nice signature that we're seeing of these very low energy modes. These are gigahertz modes, which we call phasons. We take this nomenclature. When I say we, it's ours and Manish's group. We take this nomenclature from quasicrystals and charge density waves. All right, so let's get started with the fun. So already Ananda and Chandan and I think a lot of people have already mentioned this 2D material. So, but if I want you to take one thing from this slide, is just think of these 2D materials as sheets of paper. Okay. So as it's difficult to tear a sheet of paper than to stack a sheet of paper over the other, 2D materials are like sheets of paper. And the interesting thing because they are sheets of paper and they have these van der Waal bonding between them, you can stack one 2D material on the other, and you can get exotic properties like the ones that Chandan and Anindya already talked about. The thing that we're interested in is they have tightly bound excitons. So excitons are these electron-hole Coulomb-bound pairs, and what's interesting in 2D materials is the exciton binding energy is so strong that they are present even at room temperature. So that's why the field started in about 2010 and has just exploded after that. Okay, so already you might be feeling bored seeing this sort of structure, but bear me a moment. So here you see these blue and red lattices, right? So this is a blue and red lattice, and I'm just going to twist them on top of each other, and what you will see is, as a function of twist angle, I hope this works, you see at larger twist angles you get a smaller Moire pattern. At smaller twist angles you start getting these larger Moire patterns. One way to think about this is that the Moire acts as a magnifying glass, okay, into your lattice structure. If I freeze these frames, if I go to higher twist angle, I get these lower Moire patterns, smaller Moire patterns. At smaller, I get these larger Moire patterns. Already Chandan mentioned this kind of stacking, and so this is the different high symmetry sites in this Moire lattice. And what people figured out, so you can already see the problem here in calculating these sort of systems. The number of atoms is huge, right? So you can't just go in and start doing DFT. Of course, you can ask a theorist to do DFT on this and they will scream at you. But what people figured out is a lot of the low energy physics is actually at these high symmetry sites, right? So if you can figure out what's happening at these high symmetry sites, you've got a pretty good understanding of what's happening. And one natural conclusion from these sort of high symmetry sites is that the Moire potential actually is symmetrical. So when I say symmetrical, it's actually periodic. Sorry, not symmetrical, it's periodic. And that periodicity is changed by the twist angle. So because there is this sort of potential here, you can localize excitons here, right? So these form these bound interlayer excitons, which I'll mention in a bit. If you want to be more formal, this is the full twist angle plus lattice constant relationship with the Moire period. As you change the lattice constant difference and as you change the twist angle, the Moire period is tunable, and that's really amazing. So you get this like one system fits all kind of approach, right? So you can either change the twist, you can either change the two materials you're looking at, or you can change the twist angle. All right. So since this is a mixed audience, I'll just briefly tell you about excitons in the system. So there are two kinds of excitons. So the simplest one are these intralayer excitons. So if you forget about the second layer, if you just look at the first layer, the excitons that you see are intralayer excitons. Intra just means within layer, right? So And the other excitons that you can get is when you stack two materials which have a type 2 band structure on top of each other. So what happens is the electron relaxes to the lowest conduction band and the hole relaxes to the upper valence band, thus forming this interlayer exciton, right? So for the purpose of this talk, I'll refer to the intralayer excitons as IALX and the interlayer excitons as IELX, okay? And the two materials we'll look at today primarily are WSE2 and WS2. So WS2 has a 2 eV band gap, optical gap, and WSE2 has a 1.65 eV optical gap. The actual electronic band gap is about 300 MeV above these energy scales. So what you can already see is the rich physics in the system by just this simple picture, right? Because these intralayer excitons are now confined in plane, whereas the interlayer excitons are between two planes, their physical properties are completely different, right? So you have this static electric dipole of the IELX, which is in plane, and for the IELX, it's out of plane. Because of this out of plane nature, the lifetime of this IELX dramatically increases, right? So compared to a simple picture of this IELX in a monolayer WSE2 system, this could be about 1 to 5 picoseconds, 1 to 100 picoseconds. IELX is about 3 to 4 orders of magnitude higher, right? So these are very long lived states. Okay. So this lifetime that I'm sort of mentioning here is for the IELX in a monolayer WS2 or WSE2 system, right? These are typical sort of numbers. But one question that we wanted to answer was, what is the effect of this of the moire on the intralayer exciton? Okay, so that was the primary question that we wanted to answer, and this had been addressed in a couple of ways. So let's look at what the theory says first. So you can create this sort of moire structure of this WSE2 WS2 moire superlattice. I should mention that the WSE2 and WS2 have a lattice constant difference of 4%, right? So primarily the reconstruction of the kind Chandan mentioned is not expected to occur in such large lattice constant difference samples. But the physics does change when you change the twist angle, as we will see. Okay, so you can do a very not a simple calculation, but a calculation for the strain distribution for this kind of stacking, as Chandan already sort of mentioned. Because of the strain distribution, you start getting this kind of effective moire potential, which I alluded to in how this sort of traps these excitons, right? So you get this about 60 MeV sort of potential, and in between you can see a 20 MeV. So if you want to compare from max to min, you get about a 80 MeV moire potential. Of course, this is for WSE to WS2 system. Different systems could have a different moire potential. Now what this leads to, because you've created this different moire potential, you have created a potential with a different length scale, automatically you have a modulation of the band structure. So the Brillouin zone actually folds. This gives rise to the rich physics. So let's look at what happens when this system for WSE2 WS2. So here we're just borrowing this paper from Meet Naik and Stephen Louis and Feng Wang's group, and what they did was they just looked at a large twist angle sample first. So remember, for most of this presentation, I'm only going to talk about WSE2 WS2 systems. So when they have a large relative twist angle, you see this boring one exciton peak, which is just a effective A exciton kind of peak. But when you start reducing the twist angle, this feature evolves into a 3 peak feature. Okay, so this is a reflectivity curve. So I'm looking at reflection contrast, so sample minus background, as a function of energy, right? So this is just white light steady state absorption. So I get these 3 features, and of course this is not a traditional sort of splitting of the peak. This is because this very nice work in 2022 said that these peaks are actually coming from the hybridization between different bands. Okay. What they also started telling us was these 3 different peaks have different spatial localization, which I'll now show. Okay. So this is the microscopic nature of these different moire excitons. So let's look at the boring part first. Okay, this is not the boring part, but this is a more simpler to understand part. So this is the peak 1. This is my primary sort of exciton peak here. So I look at this peak 1. So some calculations were done in 2022 paper, and the rest of them were done in our paper, which is on arXiv now. So let's take a step back and look at what this calculation is doing. So what I'm doing is I am locating the hole here with a cross sign. That's my blue cross sign. I'm freezing my hole there, and I'm looking at the electron distribution function around the hole. Okay. Remember what I said, that all the physics lies in these high symmetry sites, right? That's what I'm doing. I'm locating the hole here, calculating the electron density function. I'm locating the hole here, calculating the electron density function, and so on, right? So what you see here is that if I locate the hole here at the AA site, the electron distribution function, or this is actually an excitonic picture, the exciton is wholly localized at the AA site and nowhere else. Okay. Whereas when you do it on the BSEW site, which is the selenium on top of the tungsten of the bottom layer, you see that there is no distribution at all, right? Similarly, at this BWS site, you see that there is no electron distribution, right? What this means is my peak 1 is wholly localized at the AA site. Okay. I carry this forward to my peak 3. So peak 3, I do the same thing. I fix my hole here at the AA site, and then I calculate my electron distribution function, and I see something completely different. I see that the electrons are actually sort of away from this hole. Okay. In the middle part where I'm locating the BSE, the hole at the BSEW site, the contrast is even stark. So now you can see if I localize the hole here, the electron distribution function is completely apart from each other, right? So this is so-called in-plane charge transfer peak. Okay. This was very nice because by creating this moire, you have completely changed the nature of this exciton, this intralayer exciton. So it's not a small perturbation. It completely changes the dynamics. Okay. Or nobody's measured the dynamics, so we wanted to measure the dynamics. For peak 2, you can think of it as sort of a hybrid between peak 1 and peak 3. So you get this some co-localization of this sort of peak, but you also get this charge transfer peak. And this sort of unique nature of peak 2 will help us to understand some more physics. So in summary, this is this Wannier exciton kind of physics here for the peak 1, partially Wannier like and charge transfer for peak 2, and a completely charge transfer like exciton for peak 3. So this already will motivate you what is happening to these excitonic systems when I try to measure the lifetimes. Okay, so these are the two questions we started with. We wanted to probe the dynamical behavior of these moire intralayer excitons beyond charge transfer to interlayer exciton, and then we wanted to see if there are some many body complexes here in the system. Okay, so enough introduction. Let's look at what measurements we do. So we have this HBN encapsulated WSE2 WS2 heterostructure on a sapphire substrate. Here I should mention we do measurements in transmission. Here we do measurements in transmission. So because the reflectivity actually introduces a phase, so we want to get rid of that. So the measurement that we do is a pump probe measurement. So okay, so because not everybody would have looked at this pump probe measurement, so I'll just walk you through it. So imagine a pump pulse, a pulse of light. It's a femtosecond or a picosecond pulse. This goes and is incident on the sample, and we want to understand what dynamics are there because of this pump pulse. So we have this probe pulse which we delay with respect to the pump with a simple mechanical delay stage. So you can think of it as a stopwatch. Okay, you start the stopwatch with your pump, and the probe comes in and says, all right, where are my excitons located now? Okay, so a typical curve looks something like this. Okay, so transmission, the pump excites, and then slowly it decays. So this is a function of, if you fit an exponential to this, you'll get a function, you'll get a pump probe lifetime curve. Okay, so so let's look at what happens in our system. So this is a steady state transmission plot. You look at these three different excitons. So now what we'll do is we'll look at the pump probe dynamics of 1, 2, and 3. So so already in this sort of detailed pump probe scan, so on the x-axis I have delay time in picoseconds, and on the y-axis I have this change in transmission from 0 to 1. Okay. So let's look at peak 1. It's one of the simplest to understand. So peak 1, there's this sort of coherent artifact initially, what we think is a coherent artifact. And then you have a very slow dynamics. So the peak 1 decay is about 1000 picoseconds. Remember, for a monolayer WSE2, the lifetime was about 5 to 100 picoseconds. So this is already about at least an order of magnitude, if not more, the lifetime of this peak 1. Okay, so the moire is dramatically changing the lifetime of these excitons. The peak 3 has this large background, which is indicative of a very long lifetime. So the peak 3 is actually very long lived. We don't really measure really a decay curve for the peak 3. But what we observe in peak 2 is something even more remarkable. So already this lifetime, nobody has measured this, so we're the first people to measure this sort of lifetime. The second remarkable thing about this, this measurement was this sort of oscillation. Okay, so as a spectroscopist, whenever I see a new peak or some oscillations, that at least gets me excited to understand what's the underlying physics here, right? But the remarkable part here is that these oscillations are, at least in terms of ultra-fast science, are extremely slow. Okay, so these oscillations are of the order of about 300 to 500 picoseconds. Okay, so if we, so we'll get back to these oscillations in a bit. But first, I'll just take a brief detour to explain why are we able to measure this. So you may realize this if I go back to this sort of slide here, that my interlayer exciton is the lowest energy state. Okay, so my charge transfer, if I look at the system in the equilibrium, all of my electrons will go into the WSE2 and all of my holes will go into the WS2. So I should form a interlayer exciton all the time, right? So why are we able to measure this beyond this ultra fast charge transfer? So what we think is happening is the interlayer excitons, we are saturating it. So let me explain how we're doing that. So if I probe this interlayer exciton, the PL of this interlayer exciton, within 10 nanoseconds it doesn't decay. But if I change my repetition rate of laser, I see that the interlayer exciton is able to decay with a period of about 200 nanoseconds. Okay, so you can imagine the system. You create a population of excitons in WSE2. It relaxes to the WS2. It creates this interlayer excitons within 100 femtoseconds. Okay, the charge transfer is extremely fast, but the lifetime of these interlayer excitons is extremely long. Okay, so the physics that you measure is usually the interlayer exciton. So why are we able to do this in our system? So what we do is we have a pump probe system where the lasers, each pulses come after about 12.5 nanoseconds. So what we're doing is we're not allowing this interlayer exciton system to relax down. Okay, so we're sort of saturating the system when we are repeatedly pumping the system. Okay, so it forms this sort of background population of interlayer excitons. However, if, for example, like in this system, we allow the system to relax between the two pulses, then we are able to measure the intrinsic lifetimes. Okay, but in this case, we will not be able to measure the intralayer excitons. Okay, so this is the crucial part. This is the reason why we are able to do all this physics. Okay, so one sentence summary for this is higher repetition rate is required to measure IELX dynamics beyond this charge transfer to IELX. Okay, so now let's go back to this oscillations that I was showing, and which at least in my mind is the most exciting part of this work. So what we did was we wanted to understand where these oscillations are coming from. So the simplest thing what we can do is we can change the relative circular polarization of the pump and probe. Okay, so we change this relative circular polarization, so we can do co-circular or cross-circular, and what we see is that the oscillations are nearly the same. There is no circular polarization dependence. Okay, so this is for one of our devices, D1, which is 1.7 degree, and then we create another device, D2, and D2 has a twist angle of 0.2 degrees, very small twist angle, and here the oscillations slow down. Okay, so if I take an FFT of these oscillations, in the higher twist angle case, I get a higher frequency of 5 gigahertz, whereas for the smaller twist angle, I get a smaller frequency of about 1 gigahertz. Okay. So what's happening? So one sentence summary of this slide is the oscillations are polarization independent, they are twist angle dependent, and they are extremely low energy. How low? Gigahertz, right? So if you calculate the energy scale of this is about 10 to 20 micro EV. Okay. So here I would like to introduce you to this concept of phasons. So this is sort of a timeline for these phase-on pictures. So they were, I would say, discovered around 71 in these incommensurate systems. So incommensurate means like there is some periodicity, but it's extremely long period. So for all practical purposes, you can think that there is no periodicity, which happens for these very low twist angle samples. So they in charge density waves, there was some theoretical origin here, and then right around 1985, they were called out to be this core hydrodynamic mode for quasicrystals. Okay. In 2019, people started exploring them for, I think this was a theory work in twisted bilayer graphene, and you can see this Moiré pattern fluctuation, and you can see this periodicity here. And then from a theory collaborator, Manish's group, they calculated these phasons, and they were ultra soft modes, very, very low energy. The energy is actually almost impossible to calculate. Okay. So what was interesting was, after all these theory sort of proposals, in 2025 there was the first sort of experimental observation of these phase-on modes in transmission electron microscopy, right? So they used a method called electron tachography, and what they were doing was, this is very cool. So they were looking at these different domains, right, as the way Chandan explained, and what you can see is here in this sort of colorful area that these atoms look stretched, right? So these atoms look stretched, which means that they're actually oscillating about their point. So they were able to model this, whereas for the other sides they're almost spherical, which means they don't have this high displacement vectors in plane. All right, but of course this is all sort of static measurement theory. So what happens to what is the energy scale of these phasons? What are the dynamical interaction? This is the question what we wanted to answer. So we went to Manish again for some theory calculation. So let me play this picture. It's a very beautiful picture. So what's happening in this is, of course, there's theory work. So there are these atomic sites, right? So red and blue atomic sites, and the way to think about these sort of phase-on modes is, of course, we've looked at this twisted angle, right? So when you create this twist angle and you create a Moiré pattern, if you can slide this Moiré pattern, right? So in this plane, you can slide this Moiré plane in the Moiré pattern. This is actually extremely low energy, right? The energy is very low because these are super lubric modes. I'll play this again. This is exaggerated. The motion is exaggerated here, right? But what we can do is we can calculate the displacement vectors for these modes here, and these modes have higher sort of displacement along the AA, a little bit in the BAC W side, and so there are these localized phase-on modes in this WSC2 layer. Okay, and what's beautiful here is that with the twist angle, these phase-on mode actually increase in energy, which is what we are also seeing. Okay, so we think this is a very good explanation, and this is the first time anybody has looked at these exciton phase-on coupling in a dynamical picture, right? So this is the first time anybody has done these kind of measurements. Okay, there's one more sort of detail. It's actually not a detail here, but maybe for this audience, what we can also do is we can do full two-color pump probe sort of spectroscopy. Pump energy we can vary on the x-axis, probe on the y-axis, and we can do again co-circular and cross-circular polarization. So on the this diagonal, this is the boring degenerate energy plot. But what is beautiful about these measurements is we can look at this induced absorption peak here. This is a biexciton peak. So what this means is the pump comes in, excites the system, the probe comes in, and the probe, instead of reduced absorption, it actually absorbs more. So you're able to create this higher order excitonic complex, which is called a biexciton, and this is a Moiré intralayer inter-valley biaxion. It's inter-valley because when we having pump and probe cross with each other, we are able to generate this. And the binding energy is about 16 MeV. So this is the sort of atomistic picture of how this biexciton looks like. There are two excitons in different valleys, and they form this sort of state. Okay, the binding energy is about 16 MeV. Okay, and you can, if you're interested, you can use this as a quantum simulator. Of course, we don't mention this at all. Okay, so I'll skip all this stuff. We also create 2D materials, 2D magnetic materials. We are able to grow some nice centimeter scale films. If you're interested, we can chat more. But these are the people who actually did the work. Ranju is the lead and really the reason why this work is here. And then Manish and Meet did the theory work, and of course everybody gets HBN from these Japanese gentlemen. With that, thank you.
So let's talk. So I mean, this decay measurement of your doing. I see the negative signal you see.
Yeah.
How can I understand this? Because how can I have a negative?
Right.
That's the first question.
Yes.
Second, your energy scales look like still tens of microcoulomb if you convert to the gigahertz.
Yeah, tens of like about 10 to 20 micro EV.
If you look at the theoretical calculation, 1
Yeah,
centimeter.
that's right. Absolutely.
That's at 1 order of magnitude high.
That's absolutely correct.
So that's I see the difference.
Absolutely correct. So first, let me answer that question. So actually, the energies, if you talk to Manish also, the energies calculated for the phase-on modes should not be taken for the magnitude. But what we should look at, because the energies are actually below the theory error bar. Okay, so they are very low energies. All right, and but what's important to notice is the trend with twist angle. The twist angle, with twist angle, the energies actually increase. That's also what we see. So I would urge you not to look at the absolute numbers for the energies. Those we also say in the paper that the energies are not to be calculated, to be compared directly. Yeah.
But this negative.
Yeah. So in pump probe, it's great question. So in pump probe, it's not very easy to directly say if a positive is bleaching or a negative is. So you actually have to look at the full 2D pump probe signal, like the one that I sort of this sort of this whole thing you have to look at in one shot, like, because let's say this feature starts shifting energy, okay, it will start influencing its nearby neighbor. So you have to look at this whole feature together. You have to consider energy shifts, you have to consider energy broadenings, and that's one way that you can simulate this whole plot. So by just looking at one delay scan, it would be hard for me to say what's happening there. But
negative meaning is exciting. That's emitting some.
You should think of it as a induced absorption peak. So here you're inducing the probe to be absorbed. Okay, so the probe wants to be, usually if you are having a number of carriers, the probe will be transmitted more. In this case, it's transmitted less. Okay, so this is the induced absorption part.
Nice. Somehow I missed two questions. So somehow I missed your oscillation part. What was the explanation for that? The second one, how do you calculate your angle?
Yeah.
So I don't see any.
Yeah, we don't show all these details here. So we do both the edge. We do both the edge alignment. So we compare the edges, and then we also do second harmonic generation in a lab. So we can compare the polar plots and see what is happening. The oscillations we attributed to phase on these very low energy modes. Here we are talking about these, and I didn't discuss this detail, but the peak 2 is actually what is giving our oscillations, not the other peaks, because that seems to be overlapping with this sort of displacement vector. Okay.
Hi, Akshay.
Sorry. Yeah.
Very nice talk. So one of the questions is the biexciton. How you ensure it is a biexciton? Have you done any power law behavior?
Great question. Okay. So of course, when people think about biexcitons, they want to see power law dependence. But firstly, in pump probe, you don't see power law dependence because the signal is already nonlinear. So it scales linearly with pump and probe power. So you can't do pump probe power dependence for biaxion. However, you can do PL, photoluminescence for biaxion. What complicates, we feel, in our system is this inherent sort of relaxation process to the interlayer exciton. So that's why we are not sure that we will see power law dependence there in that biaxiton. So
What is the lifetime of that biaxiton?
the lifetime for the biaxiton is about more than 1000 picoseconds. Very long lived.
Oh,
Yeah.
Hello.
Yeah. Hi.
Very nice talk.
Thank
I
you.
just have two questions regarding the palm probe spectroscopy. So, you use any microscopy
Yeah.
like this?
Absolutely.
So, how you get rid of the pump?
Great question. So we actually, one sentence summary of what we do in our lab is we do transient and steady state absorption in PL with a 1 micrometer spot size. So we can do everything on the same spot, on the same sample with a 1 micrometer resolution. So we have the setup for that.
So, what is the numerical aperture?
The numerical aperture is about 0.5. 0.5. We use a 50x objective, but we're very careful in how we set up the optics. Yeah.
And the second one is that I saw you go from one angle to another angle.
Yes.
So, is there any difference between the interlayer excitons?
The intralayer
So you
yes.
compared
Yes, correct. Yeah, so for the higher twist angle samples, some of the excitonic peaks actually disappear. Yeah, I think can we take one question? Shima?
Maybe I'll just.
Oh, sorry, I think there was a, okay, yeah.
If I saw your plot correctly, you have this type 1 exciton where electrons and holes are kind of localized on top of each other, right?
No, this is type 2 band structure. So the, sorry.
You have this peak 1, peak 2, peak 3.
Yes.
And you have the spatial wave functions.
Yes.
Holes and electrons.
Yes.
And for feature 1, the holes and electrons are at the same spot, right? Roughly.
Yes, correct.
With this spatial proximity, still you have such a high lifetime. I mean, how do you?
Yeah, it's remarkable, no? But we think it's because of Moiré confinement. So actually, what's interesting is if you look at the dimensionality analysis of this. So you take a quantum well, right? The lifetime is like, let's say 100 picosecond or so. You take the same system and you shrink it down to a quantum dot. You would think because the electron and hole are now more closely confined, the lifetime would be shorter. It's actually longer. Okay, so I think it's a density of states argument there.